were talking about what equilibrium is, and the idea is that the reactions, even if you're looking at a reaction and it looks like reactants, arrow, products, you can start with products inside of a flask, and if it's a reversible reaction, it will eventually come to some equilibrium with having a certain amount of reactants and products inside of your flask. Or you can start with just reactants, and then your reactants will change into products, and those will decrease over time. Or what you can do is you can start with reactants and products by putting one of everything inside and then see what happens and where your reaction ends up going. If you have more reactants at equilibrium, then you're favoring the reactants. If you have more products at equilibrium, you say that you are favoring the products. Okay, now what they did is they use a value, an expression, and so it's called the equilibrium expression, and it's given the symbol K, Keq. And so all that K tells you is your ratio of what to what? Products to reactants. Perfect. And so you do products over reactants. So if you have more products than you do reactants, I'll switch to the next page in just a second. If you have more products than you do reactants, then your K value would be greater than 1 or less than 1? Greater than 1. Perfect. So if your K is greater than 1, we would say that it's favoring the products. And if your K is less than 1, then we say that it's favoring the reactants. And then obviously, if it's equal to 1, then what would be true of your products versus your reactants? Perfect. They must be equal to each other. Now, when you write an expression, though, the one thing that you need to make sure that you remember that's going to keep on coming up is you are not including what two phases of substances in there? Solids and liquids, and why? Why are you not including solids and liquids in the expression?
Because they're incompressible.
They end up remaining constant. So even though it changes your reaction, they still remain constant, and so they basically put that in with the K is the way that they do that, okay? Because by adding solids and liquids, it still just ends up changing everything equally. So then they say that it's it just gets added right into your constant instead. Okay. So we talked in the beginning about Le Chatelier, and so there are 3 major factors that affect equilibrium. What are those 3? And I like doing Le Chatelier's principle, Le CTP. And his principle, I don't have principle on there. Le CTP. Everybody say Le CTP.
Le CTP.
What's C for? Concentration, changing temperature, and changing pressure. Perfect. And so changing pressure you can do by decreasing the volume of a system. So by changing the actual size of the container, for example, that can change if you have gases inside of there, then that would make a difference. Okay, so then we talked a little bit about how changing the concentration and the temperature and the pressure would affect those reactions. So remember, for concentration, if you add to one side, it's going to shift in which direction? The opposite. If you take something away? It's going to shift in that same direction. So if you take it away, put it back. Temperature does the same thing. If it's exothermic, is heat on your reactant side or is heat a product? If it's exo, it's a product. Perfect. So if heat's written on the right side of your reaction and it's exothermic and you heat this, it's similar to adding a product. And so which direction would your reaction shift? Back toward the reactants. And then if you cooled it down, that's similar to taking away heat, removing heat. And if you take something away, you want to put it back. But keep in mind that everything on the product side would end up increasing. Okay? So just keeping that in mind, that these are going to react with each other to form this. So it's not just this starts increasing. It doesn't just start increasing from nowhere. It starts increasing from these two actually coming together to form the SO3 again. So keep that in mind that as this increases, what happens to these? They decrease naturally. Okay. So just remember, because one of the biggest misconceptions is a lot of students want to separate the reactants from the products as if they're in different flasks. They're not in different flasks. They're in the same flask. So just making sure that you keep that in mind. Okay, and then pressure. I use the more is less and less is more. So what does that mean? More pressure, if you add more pressure, you want the side with less moles. Awesome. And then the opposite, obviously, is true too. So that's for pressure. And when you count your moles, you do not include solids and liquids again. Okay, so make sure that you're not including the solids and liquids when you do that. All right, and then we did some of those problems. Then we started talking about the value of K that we were just reviewing a moment ago. We said don't include the solids and the liquids. there's a Kp and there's a Kc. Typically, you just call it K or Keq, okay, the equilibrium constant. So Kc is what we're talking about when we do concentration, and typically you're going to have concentration values. You're going to have molarity values, okay? But if you have a gas, then you're not going to talk about having the molarity of the gas, right? Instead of having molarity and using concentration, what would you talk about for a gas?
Pressure.
It's pressure. And typically what they'll use is they'll use atmospheres of pressure. And so what you end up doing is if you need to convert and you're given the Kc value and you need the Kp, for example, I call it the what equation? Curtin equation. So there's your curtin right there. So it's KcRT delta N. Your R in this case is for atmospheres, so it's the 0.0821. Perfect. Your temperature must be in Kelvin. And then what's delta N?
Change your moles.
Products minus, yep, your moles of your products minus your moles of your reactants. And so it's going to be a whole number, 2 minus 1, 3 minus 2, whatever that is. And then you just multiply that. Make sure you're not doing K also inside of this, so it's RT raised to the delta N. So just keep that in mind too. Okay. And so then you can switch in between those. Typically, you can see that we just call it Keq, okay? We just call it Keq. Even though we're writing these as concentrations, they can be written as pressures as well. And so you would write it, for example, as pH2, P, the pressure of Br2, divided by the pressure of HBr squared. So that's how you could write this in the form of Kp, okay? Good? All right. So we talked about what if we don't know the concentrations of all the substances in equilibrium, then we can use what to figure one out when we stoichiometry. Okay. The only thing is that you would have to use it for one side because you may not be starting with any of the product. If you're starting with a certain reactant, your reaction will not proceed unless you have all of your reactants present. Do you agree?
Yeah.
Yes, right? So you have to have all of your reactants present there in order to proceed. Well, so you can't just say, I'm just starting with Br2 when my reaction is Br2 plus Cl2 yields something, okay? So you need to make sure that you have equal amounts, at least, of the two of them. So sometimes you can assume that that would be the case, but you're not assuming that you have made product yet, okay? You haven't come to equilibrium yet. Some problems are going to say, at equilibrium, blah, blah, blah. Or they'll give you information and they'll say, for this reaction, the equilibrium constant is. You can assume then that you're at equilibrium. And I'll try to be very clear, and typically the AP is really clear about whether you're at equilibrium or not. And the way that you're going to solve the problems are very different whether you're at equilibrium or not at equilibrium, okay? If you're at equilibrium, the problems are really easy, and it's similar to what we did here. You're going to use an equilibrium expression. You can write your products over your reactants, and then you can plug in what the values are at equilibrium. The one thing is, you have to be at equilibrium in order to use this, okay? So if you're not at equilibrium and you're using random concentrations, we're going to call that a different letter. It won't be K. It'll end up being, anybody know the reaction quotient? What letter they use for it? Q. Nice. They end up using Q, and we'll talk about Q today, okay? So Q is when you have random concentrations. What we're going to do today, though, first is we're going to talk about what are called ice boxes, and how if you're not at equilibrium, or maybe one thing's at equilibrium and the other ones are not, how are you supposed to figure out those concentrations? And so some people don't even use this box, but it's a really, really nice way of organizing things. Okay, so we've done question 1, and we did question 2. Let's just take a look back at question 2 here. Same thing, in this case here, we figured out what the molarities were of the Cl2 and the Br2. We were looking for the concentration of BrCl at equilibrium, and they gave us our expression, or the constant value. They gave us our Keq, and so we solved for the BrCl. So watch what happens now. Number 3, so I want to make sure you understand the difference between you're at equilibrium versus you're not at equilibrium yet, okay? That's going to be the biggest thing in the difference with these problems. Those are really easy. These get to be more difficult. Sulfur trioxide decomposes, and so we have this reaction here. And initially, the vessel is charged at 1,000 Kelvin with SO3 at a concentration of 6.09 times 10 to the negative 3. At equilibrium, really important that you see that word. Once you see that, circle it, underline it, squiggle it, whatever you want to do. Okay, so at equilibrium, The SO3 concentration is that. Calculate your value for Kc at 1,000 Kelvin and follow the steps above. Okay, so let's start off first by writing our expression. Okay, so our expression is Keq is equal to concentration of the products over the concentration of the reactants. So somebody want to guide me on this? SO2 squared plus what? Times O2. Awesome.
Divided by SO3 squared.
Nice. Perfect. Okay, first step is going to be to write your expression. Okay, so make sure that you do that as your the very first thing that you're going to do. All right, so what do we know? We know SO3 is at a concentration of that. Is that at equilibrium? No, they say initially. So this right here is an initial value. All right, that's not at equilibrium. Then this is at equilibrium what your SO3 value is. Okay? So we're going to calculate the value. So what could we tell about SO3? What could you tell that could be important here? How much it what by? It changed. Perfect. We can tell how much it changed by. And I'm going to tell you that the only time the stoich works at the change step. The stoichiometry is going to be equal during your change step for your reactants versus your products, because if you're creating products and you have a certain number of products that you've created, well, it took reactants in order to create those. Your initial amounts don't have to match. Again, why do your initial amounts not have to match? Why does it not have to match stoichiometrically? You're not at equilibrium, and I could put whatever I want into the flask. So it doesn't have to be stoichiometrically correct, because I just put in there whatever I wanted to. And at the end, it may not work stoichiometrically either. Why? Why is it possible to not have at the end your actual concentrations inside of your flask? Why is it possible for them not to work stoichiometrically in the end? To end with equal amounts, because why? You may actually have something.
Limiting.
Okay, perfect. Limiting and excess reagents. Awesome. So you may have something that's extra inside of there, and so you may have some stuff that's left over after as well. So that's possible too. So just keeping that in mind, that doesn't have to work. What has to work stoichiometrically is what is called the change step. So let me introduce the icebox next. Question. Okay, so let's write the reaction first. So I have, let's write our reaction. So we have, and you're going to need room for a box. I'm just going to write the same reaction that we have up there. So I've got 2 SO3, and then I have my double arrow, and I'm going to have my 2 SO2 plus my O2. Yes. Okay, I'm going to create a little bit of a box here. And I'm going to write ICE. Let's make that a hard line. And let's make that a dotted line for the reactants. Bless you. My I. There's my C. There's my E. Okay, so what we're going to do is we're going to write what we have initially. Fill in anything that you have on here, okay? So I stands for what? Initial. So I equals initial. C equals what? Nope. That's your change step. That's how it changes. So that's your change step. And what do you think E is for then? At equilibrium. Awesome. Okay. Our goal, our target, is to be able to get to equilibrium, because once we have our equilibrium values, what can we do? Solve it. We can throw those in there. Okay, but not until we have our equilibrium values. So what do we know? Initial of SO3 at 6.09 times 10 to the negative 3 molar. So our initial SO3 right here is 6.09 times 10 to the negative 3 molar. And I'm going to double box it because I like to show the difference between what I found versus what was given to me in the problem. What else were we given in the problem?
Equilibrium.
Perfect. The 2.44 times 10 to the negative 3 at equilibrium for the SO3. Okay, so what can I do now?
Figure out the change.
Subtract. Awesome. Please go ahead and subtract and tell me what you get. Like 3.65 times 10 to the negative 3?
Yeah.
So we're subtracting here, so it's 3.65 times 10 to the negative 3 molar. The minus and the plus will be important when you're given amounts of reactants and products. Typically, we say that what will happen to your reactants over time? They're going to decrease and your products will increase over time. The only thing is that if you're given all three amounts and you don't know where equilibrium sits, it can shift in either direction. So the plus and the minus does actually matter here. It does make a difference. The only thing is, if you're losing reactants, then you must be gaining products. If you're losing products, you must be gaining reactants, okay? So it's not just going to disappear into whatever land, okay? So just keeping that in mind too. All right, so if here I'm losing the 3.65, we're going to use our stoichiometry now only at the change step. So the stoich only works at our change step, okay? So the stoich only works there. So if that's negative 3.65 or 0.00365, what's this one? Same thing. Nice. Why?
Because it's a ratio.
Perfect. The ratio is the same. It's a 2-to-2 ratio. Are you subtracting or are you adding? Adding. Perfect. We're adding that. Because we're losing reactants, we must be gaining products. So then what's this one?
You divided by 2.
Half of it. Awesome. Which ends up being 1.83 times 10 to the negative 3. And we're adding that too. Well, the question is, what are we adding it to? If initially we started with this, then how much of this and this do we actually have initially? Everybody.
0.
How much? 0. This must have been 0 molar to start if initially we only have this. Okay? So it's what did you put in your flask initially? That's what does it look like before you actually start your reaction? So then what is the answer to this? 3.65 times 10 to the negative 3 molar. And this one would then be 1.83. Good. Times 10 to the negative 3 molar. And guess what we can do now? Plug it in. Perfect. We're going to plug these right in. Don't forget to make sure that you're using that square on that. So we're going to use the SO2 at equilibrium is 3.65 times 10 to the negative 3 squared times my O2, which is the 1.83 times 10 to the negative 3, divided by the 2.44 times 10 to the negative 3 squared. So again, don't forget your square. Go ahead and calculate it, and please tell me what you get. Don't forget your squares. I want you to make sure that you try to calculate it. Get 4.10 times 10 to the negative 3? Yeah. Perfect. Units of this K, there are no units of this K. Okay? This K doesn't have any units. What does this mean? If it's less than 1, you're favoring reactants. Perfect. At equilibrium, reactants are predominating, meaning that they're being favored. You have more reactants inside of your flask than you do products at equilibrium. Good? Okay, let's go to where I have Q4. All right, so in this one, they're giving us moles, but it's in 1 liter anyway. So even though they give us moles, we can use 1 molar. You can use moles as long as you use moles throughout the entire thing. And then if you need molarity, you can just divide by liters. So it says that we have 1 mole of the H2 and 1 mole of this violet iodine vapor, and they're sealed in a flask, and then they let it react at 450 degrees. Are we at equilibrium?
No.
No, we're not at equilibrium. That's the hard part, is making sure that you get, are you at equilibrium yet or not? If you're not at equilibrium, guess what you're going to need? An ice box. Awesome, you're going to need an ice box. Then it says at equilibrium, so underline that, squiggly line it, or whatever you want to do. Now we have 1.56 moles of this hydrogen iodide, and it's present together with some of the reactant gases. Calculate your KEQ for this reaction. Okay, so we're looking for KEQ. Again, step number 1 is write your expression. Okay, so our expression is HI squared, right?
Yeah.
Over
H2.
H2 and
I2.
I2. Okay, so let's do the same thing that we did before on this side. Okay, so I've got H2 plus I2 yields 2HI. So write it out first. Okay, I know it's like doing it over again. If you wanted to, you could have left space there and just done it from there. And so then what we're going to do is we're going to write ICE. And draw your lines across. And then I do a dotted line between the reactants, and then I do a hard line between the reactants and the products, just so that I can see the difference between reactants and products. Okay, so we know what initially, or what do we know? Because maybe they don't give you, sometimes they give you at equilibrium.
We know the initial of H2.
Perfect, and that is 1 molar. And the I2 is 1 molar. Awesome. If they didn't tell you the I2 and they just told you they initially charged it with H2, that wouldn't make any sense, okay? So you would just assume that you're reacting an equal amount of the two of them if that were the case, stoichiometrically, okay? All right.
We know the
equilibrium. Perfect. You know at equilibrium, you have 1.56 of the HI, right? So then divided by 1 liter, so 1.56 molar. Awesome. So I'm going to double box these in, just indicating that this was the information that I was given to start. Okay. If you're initially charged with these two, then how much of your product do you have? 0. Awesome. Which means I can now figure what out? The change right here. So you're looking for one of the change steps. Once you figure that out, you can figure the rest of them out. So then my change must be plus or minus? Obviously plus. You're not going to have negative concentrations of something, okay? So that must be plus 1.56. All right, and if this is plus 1.56, then these two would be minus
7.78.
Perfect, minus half of it, so minus 0.78. Awesome, so minus 0.78 molar and minus 0.78 molar, which gives us 0.22, yep, thank you, 0.22 and 0.22. And now we can plug it in. Okay, so now we're just going to plug everything in once we have our equilibrium values. So our HI is 1.56 squared divided by the H2 times the I2, so 0.22 and 0.22. And so we end up getting 50 point. With this would be 2 sig figs there, so I would just say, and maybe it would have been 3 if we did 1 mole. That's really like 1 sig fig. I'm just going to say 50 point on this, which means that you're favoring what? Products. Good. Favoring products if it's greater than 1 at equilibrium. Good? Here comes the fun parts. Okay, so now let's go back to Q5. Okay. So it says, assume that the reaction H2 and F2 has an equilibrium constant of. So let's first just write our expression, because we know we're going to have to do that anyway. So KEQ is equal to, again, we've got HF squared over H2 times F2, no solids and liquids in there, so we're good with this. And we know what it's equal to. We know that the value of this is 1.15 times 10 to the second is equal to this. So when we come back to fill that in, I'm just going to put that in there so that once I come back to fill it in, I don't forget that I already have that. Okay, that's not the variable that we're looking for. In a particular experiment, 3 moles of each component was added to a 1.5 liter flask. This is really important. Each component, each substance. What do they mean by each component? They didn't say each reactant.
They're all.
All of them. All of them. And that's really important, okay? So all of them are being added in. Are we at equilibrium?
No.
No, we're not at equilibrium. We want to figure out what happens at equilibrium. So we're not at equilibrium yet, okay? So the first thing we're going to do is write our equation out. So again, we have this H2 plus F2, the 2HF. Write your I, C, E. Draw your lines in. Again, dotted line between the reactants, solid line with the products. Okay. You can use moles, but we want concentrations of them. So if we want concentrations, may as well just switch to molarity right now, that we don't have to worry about it later. So what's 3 moles? How do I find out my molarity? Moles over liters divided by the 1.500 liters, which means we have what molar? 2.00 molar with 3 sig figs. Okay, so that's our molarity. And that's of each one. So I've got 2 molar, and 2 molar of each one. Okay, good so far? All right, so the difference is before they didn't say of each one, now they're saying of each one. We don't know which direction our reaction's gonna go. So what we're gonna do is, we're gonna calculate Q, the reaction quotient. And what Q is gonna do for us, actually you're gonna tell me what Q does for us in just a minute here. Q looks just like K, all right, except you're using random concentrations. So Q is for random, I'm going to put random concentrations, random in brackets. Okay, so Q is for random concentrations, and it's called the reaction quotient. Okay, so let's try to calculate Q. Q is equal to HI squared, oops, I wrote F, oh that is an F. Sorry. Turn this back into an F, F2. Okay, so we have Q is equal to HF, which is 2 molar, squared, divided by 2 molar times 2 molar. Which means that Q in this case is equal to what? 1. Okay. What do you think you can do with Q? And I'm going to tell you that it's similar, supposed to be like K, right? We did everything the same way that we did K. What do you think we're comparing it to, Ben? The value of K. Perfect. What does K represent? Equilibrium. We're not at equilibrium. Here we're at a value of 1. Guess what the reaction wants to do? It wants to get to what? Equilibrium, which means we're trying to get to K. I keep losing numbers here. So what's going to happen is this is going to change to get to K. The question is, and there's an easy way to remember it, the question is, this needs to increase, right, in order to reach 115, 1.15 times 10 to the second. How is it supposed to increase? How does this number get bigger? Does it get bigger by adding more products, or does it get bigger by adding more reactants?
More
Products. Perfect. So guess which direction your reaction is going to shift in this case?
To the reactant. Right. To the products.
Toward the products, to the right, toward the products. Good, good. Okay, so the idea is that if your Q is less than K, you compare Q to K. Compare, and I have this written on the next page, Q to K. If Q is less than K, then your reaction needs to your K value, your Q value needs to increase until it gets to K. Then that means that you need to add more products because products are in the numerator, right? So you need more of the numerator added in. Then favors products, which means you're going to add on the product side. If Q is greater than K, then you've already passed equilibrium, and what does your reaction have to do? It has to decrease, it has to shift backwards, and you need to actually go back. You made too much product. Now you need to shift backwards, and your reaction is going to get back toward the reactant. So if Q is greater than K, then it's going to favor your reactants, which means you would add on the reactant side. Okay? So in this case, you would subtract on your reactants. In this case, you would add on your reactants and subtract on your products. So I'll show you that here. So here we said that Q was equal to 1, meaning that Q was less than K. So then that means that we're going to add on which side?
Product.
Add to the products, subtract on the reactants. Okay, in this case. So that's my change step. I'm going to add here on my products, and I'm going to subtract on my reactants. Why didn't we have to do this before? Yeah, you were already given one of them, and you were starting with 0. Can you go less than 0 as far as molarity is concerned? No. So you can't subtract any further. You must be adding. You can only increase. And so that's the case of when you would use Q versus not using Q. All right, so what's going to happen in this case is we don't know any of our change step. So this is what we started with, was right here. And we don't know anything in our change step. Guess what you call it when you don't know anything? X. Yay, we're going to use X. Okay? So, what's the easiest one to call X? The H2, which then would make your F2 X, which would make this one 2X. Awesome, because of the stoichiometry. So remember, this is a step that works stoichiometrically. So, now we can just write this as 2 minus X, 2 minus X, and 2 plus 2X. 2 plus 2X. Okay, so I've got KEQ is equal to HF squared. So I've got 2 plus 2X squared divided by, well, it's 2 minus X times 2 minus X. So I'm just going to write 2 minus X squared. Do not forget what you've learned in math because it will help you tremendously, okay? We already know KEQ, so I'm actually going to erase that and just put my number in for KEQ, or you can do it on the right side. So I know that my KEQ is equal to 115, okay, or 1.15 times 10 to the second. So I already know that. What can you do to, what's the easiest way to simplify this? I do not want to start multiplying, foiling, distributing. I don't want to start doing that yet.
Square root both sides.
Perfect. Why can you square root both sides? Because you can get rid of the square there. So if I square root this, then I have to square root that. And so then what I get is 115 square root of that, 7, I have 10.72 written down. So 10.72 is equal to, now I've got 2 plus 2x over 2 minus x. That simplifies it quite a bit, okay? Now what do I do? Yeah, now I have to do my cross multiplication and then figure that out. A lot of you, depending on your experience with your calculator, you can speed these up to try to solve for x, okay? 10.45 minus 10.72x is equal to the 2 plus 2x. And so then I got my x's on one side together, so I subtracted the 2 to the other side, so it was 19.45 is equal to 12.72x. And then you're going to divide by the 12.72, and I get x is equal to 1.529. I just multiplied the 10.72 by 2, and then that by the x, and then set it equal to that, and then just did the algebra with that. 1.529. Okay, now that's not done because I wanted my equilibrium concentrations. So what do I do now?
Plug in.
Yep, just plug in those values. So what does 2 minus x become? And if your answer is bigger and you get a negative, you did something wrong, okay? So if you get a negative, you definitely did something wrong. So then I'm just going to do these in a different color so that you can see. So if I subtract these, both of these will end up equaling 0.471, awesome, 0.471 molar. And then if I add the 2 plus to this number 2 times 1.529, I get 5.06 is what it looks like, 5.05 or 5.06 molar for the HF. So that's my HF concentration, and then my H2 is equal to my F2 at equilibrium. Last one. Number 6. So for the reaction H2I2, the equilibrium constant is, so they're giving us the constant. Suppose HI, okay, so let's write our expression first. So KEQ is equal to, good, and I2. Perfect. And again, we know that it's equal to 100, so 100 equals this. All right, so let's write our equation. Well, let's figure out, are we at equilibrium? So they give us the equilibrium constant is 100. Suppose that these are mixed in a 5-liter flask. Are you at equilibrium yet?
No.
No. They're just telling you that you're mixing them together, okay? So we're not at equilibrium. So that means that we need an ice box. Yay. Okay, so H2 plus I2 yields 2HI, and again, we're going to do our ICE. Dotted line between the reactants, solid line to the products. Okay, so now they're not giving us concentrations, they're giving us pressures. Why?
They're the same.
They're gases. Perfect. They're gases. Okay. So we've got the H2, the HI is at a 0.5 atmosphere. The H2 is at 0.01. And the I2 is at 0.005. Does the 5-liter flask make a difference right now? No. So you're not dividing because you're not getting molarity. Okay, they're just telling you what size the flask is right now. All right, I'm going to just double box this because that's what I'm being given. Do we have any other information besides the 100?
No.
No. So what do we need to do? If we don't have any of the change steps, then we need X. Well, we need X, right? And then we'll, yeah, perfect. Okay, so let's first figure out what X is, or what our ratio is here. So it's minus, we don't know. It's going to be X, X, and then this would be 2X. But we don't know which direction our reaction is going yet. So we don't know if we're favoring reactants or favoring products. So let's find Q. Q is equal to HI. So I've got 0.5 squared divided by 0.01 times 0.005. Okay, can somebody tell me what you get for Q, please? Awesome. 5,000 is what you get, which means Q is greater than or less than K? Much greater than K. That means you've way surpassed. You have way too many products. So what's going to happen? Yep, you're going to increase on your reactants, therefore you're going to add on your reactants and you're going to subtract on your products. Okay? So, in this case, I'm going to say plus my reactants and minus my products, which is opposite of what you would normally do. Typically, you're adding your products and you're losing reactants. So I get 0.01 plus X. I know I'm going to use 3 sig figs, so I'm just going to shorten this just to get the math, just to make the math a little bit easier here. 0.005 plus X, and then 0.5 minus 2X. And then I can use the 3 sig figs after, just to make that a little bit easier. Okay, so let's plug this in. 100 equals, I've got 0.5 minus 2X squared divided by 0.01 minus X and 0.005 plus X. So, plus, sorry. Thank you. I keep losing lines. Plus. Okay, good. So now, when we go to do this, can I square root? No. Guess what you need to use? The quadratic equation, everybody! Now, I'm going to tell you that as long as you have a quadratic program in your calculator and you know how to graph that, and that's going to be your easiest. That's going to be your best bet. Okay? So, as far as simplifying it, how much do you have to simplify in order to get it to be able to graph and find out what X is? Figure out if you can get X. I'm not going to tell you what it is. I'm going to write out what I would do algebraically, what you would get algebraically, and so from there maybe you can do that too. So, I ended up multiplying these two together and got 5 times 10 to the negative 5th plus 0.015x plus x squared is what I got for this part here. And then I just multiplied it by 100 and set it equal to that. After doing all of this, I ended up getting 96x squared plus 3.5x plus negative 0.245 after I got it all on the same side and set it equal to 0. So now, is that where you would have to get it to before you could plug it into your calculator? You'd have to get it into this form? You don't even have to do that? Can you just start it from here? Okay, so like Jacob's saying, you can just start it from there. Did you already figure out what x is?
No, but you're gonna.
Sure that you'll get when you plot it, you'll get the two x values. You shouldn't get anything less than 0. So one of the x's will make sense and the other one will not. Nice.
Yeah, I got it.
0.0354, 0.0355. So you can use the quadratic, but most people have said that if you just plug it into your calculator, it makes it so much easier rather than doing that. So I'm not even going to tell you. This is not going to be a multiple choice problem. You'll have your calculator to do a problem like this anyway. So we'll just make sure that you have your quadratic. X ends up equaling 0.0355. So using your graphing capabilities. Okay, so now we're going to plug this in over here. So when we do 0.01 plus x, okay, so here I get 0.0455 ATMs. These are different now, so this one I get 0.0405. And for the last one, when you subtract it, you should get 0.429 atmospheres. They say it's Kc. You would have to use what equation to convert it to Kp? The current equation, okay? Like on WebAssign, there's a problem where they end up saying it's K, and you can just use it also, just like we just did here. We didn't switch it into Kp because they just said that that was the constant. So we're assuming that they're telling us what the Kp is, okay? But if they specifically say that this is the Kc, then you'd want to switch it to Kp, okay? So that's the difficult thing with this is, are they talking about Kp or are they talking about Kc? Which one are they talking to us about?
Wait.
Yeah.
Isn't Q equals K?
Kq is just equilibrium constant. It can be either one.
It can be,
So when they just say Keq, they're just saying what the equilibrium constant is.
Okay.
So then it can be Kc or it can be Kp. Typically, they would, if it's usually just whichever one. If they're giving you concentrations, then you would assume that they're talking about Kc.
Okay.
If they're giving you pressures, then you're assuming that they're talking about Kp. So we talked about Q already. It says our next focus is using what we know about K to help predict the direction of a reaction when we throw in various concentrations. When we substitute random concentrations into the equilibrium constant, the result is called the reaction quotient. Awesome. That's what we called Q, the reaction quotient. And we said comparing this result to K, you can predict which direction it proceeds. If Q is equal to P over R is less than K, then to reach equilibrium, your reaction has to shift toward the products, increasing your Q. So if it's greater than K, the opposite happens and your product will be consumed, and so you're forming reactants decreasing your value of Q. So one more time, if Q is greater than K, then in that case, your reaction, you have too many products versus reactants, and that means that your products are, you have too many products. Your product concentration is too high in this case, okay? So then which way does your reaction shift if your Q is too big? It's going to go backwards. You're going to decrease, you're going to increase on your reactants, and you're going to decrease, subtract on your product side. If Q is less than K, then that means that you don't have enough product, so you want to make more product. Your product concentration is low, so then you're going to want to minus your reactants and add on your products. Okay. And this is what this box does actually. If Q is equal to K, then what? Yep, then you're already at equal. And those are ice boxes